It's now the turn of Vijay Ramnath, Vehicle Dynamics CAE Engineer at CEVT, and Adam Brandt, Industrial PhD student at CEVT. In their presentation, Vijay and Adam will illustrate a holistic, cross-functional approach to vehicle development, and how the DiM250 driving simulator has played a key role in this process, in a context where the interactions between vehicle subsystems and their complexity are increasing with electrification and autonomy.
Good evening. I hope the coffee is keeping everyone at optimum sleep angles. So, after following this conference virtually for many years, it's really a great pleasure to be here and represent China-Euro vehicle technology, where we create mobility solutions for a different tomorrow. We started about 10 years ago in Gothenburg, in the west coast of Sweden, and we are the R&D and Innovation Center for Zeekr in Europe. Our clientele also includes Volvo Cars, Lotus, Polestar, and Lynk & Co. We are about 1,500 researchers, designers, and engineers, and we are asked to think big, find a way, and inspire day in and day out. Based on the clientele, you might have guessed, we are part of the Geely Group, and apart from the brands I mentioned previously, we also have Proton, Geometry, Chow Chow Mobility, LEVC, the makers of the iconic London taxi. Our technology solutions include over 2 million deliveries of the CMA platform, the award-winning 7DCT hybrid transmission, the Lynk & Co app, one of the pioneering customer-to-customer car-sharing app, where the phone is used as a key, and more recently, our collaboration with Waymo, the Google self-driving car division, is giving us an extremely strong foundation when it comes to highly automated vehicles. The SEAM platform is ideal for self-driving system integration like the Waymo driver. Apart from that, the vast interior, the comfortable ride, puts the rider at the forefront. Now, before I move on to simulators, there is someone who wants to say hello to you all. I would like you to meet Zeekr, who is on its way to Europe. So the Zeekr 001 and Zeekr X can be experienced later during the year. Now let's talk simulators. Now we've had the DiM250 at CEVT for about 2 years now, and in no way has it been a one-dimensional tool. And like it has been mentioned even in the icebreaker event, it is definitely a multidisciplinary and multi-dimensional tool. But of course, it was natural for the vehicle dynamics group to take the lead as key user. And we were able to implement features like the classic real-time tuning, where you could adjust chassis parameters in real time and do multiple iterations. We were also able to establish tools and methods with our suppliers to exchange models. For example, we were able to exchange steering models with our supplier, and not just the model, we also got the tuning interface for steering feel. So what that did was it gave incredible insight to our steering engineers about all the 100+ parameters, and the level of maturity, even though we were on the left side of the V cycle, was really, really high. Brake-by-wire maps. With brake-by-wire systems, what you're doing effectively is decoupling the pedal and the brake actuation. So what that does is it gives you a little bit more freedom to define the pedal feel map, but also the pressure deceleration map. Imagine if you're doing it for the first time with a completely different architecture and a blank sheet of paper. It's not really easy to do. So with the help of active brakes, we had multiple workshops with our brake engineers, and we were able to start with a baseline pedal feel map and also these pressure deceleration maps, and then communicate clearly to the supplier which direction we will want to go in the future. And so this saved us quite some invaluable time, and the communication was much clearer and more efficient. We were then at a bit of a crossroads here. Should we do more vehicle dynamics, more ride-oriented, or should we perhaps try to push the usage of this tool further to the rest of the company? I mean, it's easy for some of us here to understand simulators, but it's actually, sometimes it's difficult to grasp that there is some people out there who need to work with it more to understand that. So we extended this further to HMI, ADAS, which I'll talk a little bit about later, and also motion control. One of the benefits of simulator is that you're not architecturally constrained. So you have a little bit more freedom to think long-term and big picture. So I would like to cover two topics here. One is rear-wheel steering and steer-by-wire third actuator. So what do I mean by steer-by-wire third actuator? So with by-wire systems becoming increasingly prevalent, redundancy becomes a very important topic. So how will the redundancy mechanism come in and work? How safe is it? What happens if the steer-by-wire system fails, both your fallback system and your primary system? Should I maybe use the brakes and the powertrain, which are mainly longitudinal control, to do a lateral minimum risk maneuver? Or should I maybe have rear wheel steering as a standard and use that as a natural redundancy mechanism? So these are the big picture questions we asked ourselves. Yeah, of course, I don't want to give away all the answers, but the suspension parameters that need to be changed for perhaps a steer by brake was very close to the parameters identified by suppliers who are working deeply with this topic with physical prototypes. So this is really good positive reinforcement for us that the simulator is the right tool to accelerate our function development. Rear-wheel steering in the DiM250 was a bit special because this was one of our very first implementations. So our product managers were interested in the feasibility of rear-wheel steering in a mobility type vehicle. Let's say, think operational speeds are low and you're driving mainly in cities with very tight corners. So we decided to implement this in one of our existing platforms and demonstrate and help the team understand this. So we built an actuator in Adam's car, and of course we used it to do detailed offline simulations, like turning circle, go through the packaging loops, understand how much angles we would need. And then we converted it to VI car real time. And then we took the controller development in two stages. So we started with a simple proportional controller, which would work out of phase at low speeds and in phase at high speeds. But then we also extended it to more generic driving, so into a more generic controller for stability and handling type scenarios. And we did multiple loops in a particular handling track we had. Apart from positive stakeholder feedback, this generic controller was also used for a demonstration with one of our external customers who gave us an obfuscated model. And with that, we were also able to tune they brought their expert driver over. We were able to have some really interesting tuning sessions. And they were really happy with the fact that how it reflected a really rear-wheel steered vehicle. And they were able to tune like virtual wheelbase versus wheel speed, for example. The DiM250 has also helped us take our first steps into ADAS. There was a request for a lot of videos as well, so it was good to put this in. So here you see the evasive maneuver assist. So when you're beyond the point of autonomous emergency braking and initiate a steering maneuver, this function basically helps you with a steering assist and coordinated individual wheel braking to come back into the lane. So this again demonstrates a bit of complexity in this topic, that do you just use a steer assist? Or perhaps do you use a combined braking intervention? But if so, where does the functional safety responsibility lie? But it's really great that we have this tool to evaluate these kind of complex topics and accelerate our function development. I now hand over to Adam.
So thank you, Vijay. So I'll present some material from my PhD thesis. And I mostly work with aerodynamics, but in my thesis I've coupled aerodynamics to vehicle dynamics, and one of the papers included two studies in the driving simulator that I will present here. And I titled this part of our presentation to Unsteady Aerodynamic Evaluations Using the Driving Simulator. But first I want to introduce you to my PhD topic of driving stability. So I focus on this type of driving scenario, just straight line driving on a highway. So there's no maneuvering going on. and we drive at high speed, which I define as above 100 kilometers an hour. And if you have driving stability issues in this condition, it's often some kind of vehicle nervousness that the driver describes. And you need to do these small driving corrections to be able to maintain in the straight path. This is, of course, fatiguing for the driver, and it causes discomfort for drivers and passengers. And it's something that the automotive manufacturer want to avoid at any cost, because this is not a very premium feel of a vehicle. So my topic on driving stability, in my thesis, I divided in two different subtopics, namely the crosswind sensitivity and the high-speed stability. And I did two studies in the driving simulator for these two different subtopics, so I will just briefly introduce the differences here. So crosswind sensitivity, it's an external effect, so a crosswind gust hitting the vehicle. And in terms of aerodynamics, this is mostly lateral aerodynamics, side force and aerodynamic yaw moment. And a typical example would be when we go up on a bridge in crosswind conditions and get this sudden gust affecting the vehicle. High-speed stability, on the other hand, is more of a self-induced stability effect. So depending on how we design the exterior of the vehicle, we can get some fluid dynamic or some aerodynamic effects or fluctuations that can cause this nervousness when we go at high speeds. And this is mostly vertical aerodynamics or lift forces. Furthermore, when we evaluate driving stability, this is usually done quite late in the development phase, when we take the prototype vehicles and we take them to the test tracks to go around at high speeds. And of course, we wanted to move away from testing that late in the development into earlier testing to be able to do cheaper design changes and come up with better solutions. So we want to move from the road into the lab environment. And in my works in aerodynamics, we use the wind tunnel, but also I've used the driving simulator where I can couple aerodynamics and vehicle dynamics. And also moving further on into the virtual environment with CEVT simulations and other CAE tools. So my setup for the driving simulator, I have created my own aerodynamic model in Simulink, so I can override the internal aerodynamics of the VI car real time, and define the gust that I want to subject the driver to, and I can also couple it to unsteady CFD loads, directly impose them into the driving simulator and let the drivers experience the differences. So I will go through the first study, and I will not have time to show you all the results, so if you're interested, you can talk to me afterwards. But I will show you the methodology that we used for this crosswind study. We used two different gust profiles. Profile 1, which has this going from one side to the other during the gust event, and profile 3 is a more of a step gust. We defined the gust to be perpendicular to the road, and we had a two-way coupling between aerodynamics and vehicle dynamics. So depending on the body slip angle, the orientation along the road, and the velocity of the vehicle, we can calculate the relative flow angle and the relative flow magnitude affecting the vehicle, because this is what's needed for the aerodynamic model that I have created in Simulink. And furthermore, it's been shown that most crosswind gusts occur from driving into different conditions, and it's not these local variations in time that we experience when we walk outside on the street, because we drive at so high velocities. And a typical example would be when we go up on this bridge, that we go into new conditions. So based on this, we created our own aerodynamic model, and I will present it on the x-axis. We have the distance, and here I present the vehicle to scale, but I will enhance the scale to prove my point. And on the y-axis, we have the crosswind gust. So when we drive along the road, at some point, the front of the vehicle will be affected by the gust, and we have a small time delay until the same conditions occur at the rear of the vehicle. So we use this to formulate a cause-steady model that accounts for this delay between the front and the rear. We call it a QSD model. And a regular cause-steady aerodynamic model uses aerodynamic coefficients tabulated at different flow angles. So we use that, but we also account for this delay between the front and the rear of the vehicle. We do that by defining the forces as front axle forces and rear axle forces, and we include the delay before we merge them back together. So this was about the crosswind sensitivity. So we could then subject the drivers to different gust conditions and let them evaluate the gust and what they could experience, and connect objective measures to the sensitivity of crosswind sensitivity and stability performance. Yes, I will skip through this because I want to go into the results, as said, but I will go through the high-speed stability part. So in this study, we use CFD simulations and unsteady aerodynamic results. So we have a setup where we have scale-resolving CFD simulations, and what I want to highlight here is they are extremely expensive to run. So we simulated 5 seconds of physical data, but this takes 10 days to run on a high-performance computing cluster. But in return, we get these unsteady aerodynamic forces, and we can simulate and predict the unsteady effects in the wake behind the vehicle. That we have shown in my work is very important for this high-speed stability performance of the vehicle. And we focus on 2 different roof spoiler designs. We have the baseline spoiler. The issue with this one is that when we take it to the test track and go at high speed, we do experience these stability issues. So we have the nervousness and these occasional stability issues. And then we have another version, that the improved spoiler, that solves the stability issues. And I just want to quickly go into the results in terms of aerodynamics, but I also want to highlight the problem with this, because we solved the stability issues, but at the cost of increased aerodynamic drag. So we want to avoid this penalty, and we want to understand more why we get these stability effects. And if you go into the results, we can see that in general we have slightly higher average value for the baseline spoiler, but I will argue this is not the case of stability issues. That is that we have these low frequency fluctuations from the wake dynamics that we just cancel out with the improved spoiler. And we proved this using the driving simulator. So we took the 5 seconds of physical data, and then we duplicated it, and we stitched it together so that we could have a smooth transition between the 2 or the 5 second slots. And in this way, we could create a 2 to 3 minute long session that the driver could experience the different spoilers, and we could also artificially manipulate the aerodynamic forces. We could lower the rear lift of the vehicle without affecting fluctuations. That would not be possible to do physically, to evaluate stuff independently. And we had 3 professional test drivers for this study, usually doing these evaluations on the test tracks, but now in the driving simulator, so they know how to evaluate this performance. So, going into the results, and I present this in terms of the rear lift coefficient. And on the x-axis, we have the fluctuation scaling. So if you have scaling to 1, it's the same fluctuations that we saw for the baseline spoiler. And this was blind tested and regarded as having bad stability subjectively. And on the y-axis, we have the rear axle lift coefficient adjustment. So meaning that if we go downwards, this means that we increase the downforce on the rear axle. And according to theory and previous literature, we know that if we increase the downforce on the rear axle enough, we can get a stable vehicle. And indeed, we could do that in the driving simulator as well. However, this would come at an extreme cost in terms of aerodynamic drag. Another way to solve the stability issues was to reduce these low frequency fluctuations that we saw. And we also did some to fill the design space. And for reference, I can present the improved spoiler. That has slightly lower average rear lift, but much lower fluctuation values. And from this, it might be seen that we have some trend line here that if you go above the line, we can have these stability issues, but if you go below the line, we have a green region where we have good stability performance. And also, just for fun, I did some evaluation using the simple bicycle model, and we linearized around the tire at normal loads, and saw that if I increase the rear lift coefficient enough, I can get a mathematically unstable system, meaning that I get positive real eigenvalues for this linear system. And that occurred in this location, which aligns quite well with the diagonal line. So we have a critical oversteered vehicle at 180 kilometers an hour. So to conclude, the driving simulator can be used to assess both crosswind sensitivity and high-speed stability. We saw some objective measures for crosswind sensitivity, which I just skimmed through here, but we saw that lateral acceleration and yaw velocity were good objective measures, but they were speed dependent. So the thresholds that we experiencing shift depending on the speed that we drive at. And we found a new objective measure we call a path curvature that was speed independent. We also see that the aerodynamic rear lift fluctuations greatly influence high speed stability, as I just showed. And another big benefit of the driving simulator is that we can that the aerodynamic properties and loads can be altered while driving, enabling back-to-back comparison. So the driver could press a button and compare the two different spoilers, for example. And this is a good way to investigate active aerodynamics as well. And finally, we believe that for an electric and autonomous future, these driving simulators is a very useful tool to comprehend the cross-functional sensitivity to design choices that we make as engineers, and that the DiM250 is an ideal tool to provide the needed holistic understanding of driving. So, thank you.